so let's start with number 2, and then we'll see where we need to go from there. All right. So you got, if you were to travel to a star 104 light years worth. Now, biggest, one confusion a lot of people have, light years. It's a distance measurement. It's the distance light travels in 1 year. It's not a time measurement. So, people see the word years in there and think, oh, that's time. No, it's distance, because it's the speed, the distance light travels in 1 year is its definition. What would you measure the distance to be? So, we know that if you're traveling, your frame of reference is stationary, and it's really the universe that's moving by you. So this star is moving towards you, therefore the space between you and the star is actually contracted. All right? So the star is not 104 light years away anymore. It's closer than that because you're moving. So those are the ideas that you would need in your Y. Of course, you probably want to start with, C is constant in all frames of reference. So when the star moves towards you, the length it is away contracts. All right. So those type ideas should be in your Y. All right. So So then we can grab our equations from our equation sheet, which a little bit too far. Here we go. Let's see. We're going to need our Lorentz contraction because we're looking between 2 different frames of reference. And since we're talking about length, let's grab our length contraction relationship also. So come back here. All right. So always good to remember that gamma is greater than 1. Therefore, L is always less than L naught, right? So this would be the length as seen from the ship. This will be the length as seen from Earth, because length contracts. So the ship sees this length contracted as compared to how the Earth sees it. So we just substitute in. We know, let's see, it's factors that we know. We know L is what we're looking for. L naught, in my case, is what, 104 light years. And then dividing by that is like multiplying by the denominator. So 1 minus your velocity minus 2 times 10 to the 8th. So I get 2 times 10 to the 8th meters per second over C, that quantity squared, solve for L. Let me know if you need help individually on it. All right, so we're going to start it on 7 here, where we have rock A passes Earth at this speed, same time rock B passes Earth at this in the same direction. How fast is B moving relative to A when A passes? All right, so we have a relative velocity one here. I think some of the key points to make sure you know is how many different frames of reference do we have here? Three different frames of reference. We have the Earth, ship A, and ship B. So I would even note that right in my Y, 3 frames of reference. We have the Earth, we have ship A, and we have ship B. Which one are we going to take as the stationary frame of reference? We'll take Earth, okay. And that's probably, let's look at the problem. Sometimes the problem dictates, how fast is B moving relative to A when it passes A? Okay. So that will work, but it's good because both the speeds that we have are actually, or velocities we have, are actually measured with respect to the Earth. Also should note that C is constant and absolute. In all frames of reference. Probably one of the best things to keep in the back of your mind, if you get an answer that says the speed is greater than C, you automatically know that it's wrong. All right? So it's good to acknowledge that you know that that is the fastest it can go. All right? So ladies, make sure you keep it low enough so I can hear myself, okay? I know you're doing other things, so that's fine. All right? So, let's see, where else were we? All right, I think that's probably good enough for today in there. Equation-wise, we need our relative velocity equation. And I think it's very important in here to make sure we recognize which frame of reference things are from. So the primes, we will say that those are from, let's see, we'll say those, whoops, I want this. We'll say those are from ship B frame of reference, and the non-primes would be from Earth frame of reference. All right, so this takes into account that you're looking, have measurements from one frame of reference, you're translating to another about a third, but it's good, I think, organizationally. So anything with a prime will be as it's measured from ship B, from ship A. Yes, let's say from A, rather than B. Let's go with from A. All right. And then primes would just be that. So, U would be how fast, and we'll say, let's do one other thing. We'll say B is ship A, and U is ship B. So, we have ship U, we have U here, that's how fast ship B is with respect to the Earth. So with respect to the Earth, ship B is 0.96 C. We have 0.96 C. That equals U prime, which would be the speed of B from A, which we don't know, plus B. B is the speed of A from the Earth, 0.76 C, over 1 plus U prime times 0.76 C over C squared. Oh good, we only have one variable, and so we can solve. Now, I would recommend solving not for U prime, but solve for U prime over C. Because they ask for the answer, they want to know what U prime is in terms of the speed of light, right? Now they have the little C next to the answer. So if you solve for U over C, that will give you whatever this blank is. Because if you divide both sides by C, you get u prime over c equals that value, which is going to be less than 1. Because that's the percentage of c that u prime is moving. All right? So I would divide both sides by c would be the technique I would use. Then you'll have in terms of u over c, and you just use Wolfram or something to solve it. All right? Just like we did the other class. So if you need help with that math, see me individual. I'll be glad to come over and help you. All right? It is. It is possible to put that whole thing in Wolfram. Yes, I would suggest, like we did the other day, doing substituting like another variable in for u over c. All right, so number 6, another relative motion, relative velocity one like the one we just did. So your y should reflect the same type of idea. In this case, we're going to take the spaceship as our stationary frame of reference, and then and the other thing that we need to keep in mind is that one of the directions is going to be negative. So they may be looking for a negative answer. This is number 6. We'll take the ship as stationary. So that means anything without a prime is from the ship's frame of reference. We'll take the prime from the first escape pod. So the first escape pod will also be our variable v, and the second will be our variable u. All right, and now what we really need is our equation. Oh, that's not what we needed. Got the wrong one. We need this one. So now it's just a matter of substituting in, right? So we take that, let's see. U would be the speed of the second one from the ship. And I'm going to say the second one is negative. So I'm going to say it's negative 0.79 C. So negative 0.79 C equals U prime is what I'm looking for, plus the velocity of the first, that V is the velocity of the first one, and it's measured from the ship, so that's 0.49 C. So it's in the opposite direction, 0.49 C over 1 plus our U prime again times 0.49 C over C squared. And now do the identical math that you just did on the last one. Right? And let me know if you need help with that math again. I'll be glad to do it. The difference here from the last one is that they're moving in opposite directions. So this one, the U was a negative value. And I'll double check it on my own to make sure that it's correct, but I believe